talk now is Keylogger Video Mouse, How to Turn Your KVM into a Raging Keylogging Monster by Yaniv Balmas. There has been a lot work on keyloggers already, so the question is what can be done or what can be achieved even more, and this is what this talk is about. Yaniv is a software engineer and professional in the security field. He mainly deals with analyzing malware and vulnerability research. So give a warm applause to Yaniv.
Thank you. Can you hear me? Great. So thank you very much for coming to my talk. It's called Keylogger Video Mouse, or how to turn your KVM into a raging keylogging monster. Now, a few words about the team who made this research. So first of all, it's me. My name is Yaniv Balmas, and I'm no sound. How's this? So my name is Yaniv Balmas, and I'm a security researcher. I work for Check Point Software Technologies, and my colleague in this project is called Lior Offenheim, is also a security researcher, and here is trying to understand what to do with the ampermeter. And unfortunately, he couldn't be here today, but this research is much owes him a lot for being done. So let's start with the problem. So our problem, as many other computer science-related problems, it all starts with computers, right? Well, we have computers. We have many computers. We actually have a lot of computers, you see. And when we have a lot of computers, then the thing is that each one of these computers actually needs a set of keyboard, video, and mouse in order to operate, right? Makes sense. And the problem is that when we have a lot of these computers, then we also have a lot of these keyboards, a lot of these videos, and a lot of these mice, yeah? And when a single user wants to work on several of these computers at the same time, well, this creates a big mess on his desk, right? There's all of a sudden a lot of keyboards, and he doesn't know which keyboard goes to which computer and which monitor displays what, right? Well, it's a big problem, and, well, some of you might be thinking that's not a new problem, and that's really not a new problem, and the solution to this problem is also not new at all, and it's called a KVM. Now, for those of you who don't actually know what a KVM is, so that's pretty simple. KVM simply stands for keyboard, video, and mouse, right? That's simple. And its only purpose in life is to connect one or more sets of keyboard, video, and mouse, to connect a single set of keyboard, video, and mouse to one or more computers, right? Well, it all looks something like this. You see, you have two computers underneath your desk, and their inputs and outputs are then connected to the KVM, and the KVM in turn is connected to a single set of keyboard, video, and mouse on your desk. And then you can play your favorite video game or something like that. And when you hear your boss creeping in the office, you just manage to press the 2 button, and whoa, there you go. You got a nice code on your desk, and catastrophe is avoided. And that's just as simple as that. These are KVMs. Now, where can we find those creatures, those KVMs? Well, we can find them in a lot of places. We can find them on your desktops, such as the example I just showed you before. And another thing is that we can find them in your server racks. You see, a typical server rack holds like something, let's say 8, 9, 10 servers, yeah? And in order to physically manage those servers, we must have some kind of KVM inside that rack to make the server administrator's life a bit easier, right? So we do have KVMs in server racks. And last but not least, we have KVMs in very secured environments. And the reason for that is that in those environments, we usually have a lot of networks. And those networks are a lot of times segregated or even air-gapped from each other, right? And then again comes the problem. The single user has to work on both of these networks, and in order to do that, he needs a KVM on his desk, right? This makes his life a lot easier. And if I want to sum it all up, then KVMs are pretty much everywhere. I mean, in every technologically rich environment you'll ever go to, you'll probably find a lot of these creatures laying around all over the place. Well, let's take a brief look at the KVM evolution along the years. It all started off in the 1980s or 1990s with something that looks like this. Some of you might be familiar with this, right? It's commonly known as an AB switch, right? All it is, it's a KVM, but all it is just a stupid analog box. Yeah? It just connects the electronics from the A port to the keyboard, video, and mouse. When you switch to the B port, same goes for the B port. And that's it, a stupid analog box. And that stupid analog box actually worked really fine for a lot of years. I mean, really, a lot of years. But then came one invention, one small invention that changed the world of KVMs, and I'm specifically talking about USB keyboards. You see, when you have USB keyboards, then those KVMs are simply not enough, because they will work, but when you switch ports, then the USB needs to be connected to the computer, and that has some kind of 2-3 seconds delay until the computer actually recognizes that USB. So those KVMs now, the modern KVMs, needed to implement some kind of USB stack in order to support smooth transitioning between the ports, right? And that's where we met those KVMs. Those are modern KVMs. They are really cool. This is what we see on the desks of a lot of guys today. And it supports a whole lot of inputs and a whole lot of outputs. And it's really, really cool. It also looks sexy. And then came the next evolution in KVMs, and came those monsters. Those are called matrix KVMs. They are absolutely monsters. They have thousands and thousands of ports, support stuff like KVM over IP and God knows what. They are usually implemented in some kind of huge enterprises, huge server rooms and stuff like that. And that's it. That's actually the last evolution of KVMs. Now, we come to some kind of a conceptual problem. You see, because a lot of guys, and when I say guys, I mean system administrators, security administrators, security researchers, a lot of guys still consider today's KVMs, those modern KVMs, as those same old stupid boxes, same old stupid analog boxes, right? Well, are they stupid boxes? I mean, let's take a look at some of the features modern KVM has. Look at this. They have on-screen displays. They have configurable web menus. They have all kinds of stuff like this, right? Well, obviously, those boxes are no longer stupid, right? Obviously, those boxes now run code, yeah? Well, we were thinking to ourselves, okay, so if those KVMs now run code, then what can we do with them, right? And in order to answer that question, I have another question for you. What is the one common feature between all the features I've just showed you? What is the one common thing that all KVMs share? All the features has. Well, the one common thing is that all these features actually require the KVM to be able to process keystrokes. You see, now when you enter a keystroke, the KVM doesn't immediately send it to the computer. It needs to first inspect it and see, hey, maybe this was a web menu option, maybe this was some kind of hotkey combo, maybe it was something. Maybe I need to deal with it and not the actual computer who is connected to it. And only if the answer to that is no, is false, then it will pass this keystroke to the computer, right? Well, you see, the thing is that all we need to do is to just alter the execution flow just a bit, you know, and find some kind of free memory space in there, take the keystroke, store it there, dump it later on when convenient to us, and what do we got? Yes, a keylogger. A keylogger inside our KVM. I mean, think about it. How cool is that? I mean, we know software keyloggers, right? Software keyloggers run on the host. This is not a software keylogger because there's no code running on the computer. The entire code is running inside the KVM. And this also is not a hardware keylogger, well, because there's no special hardware, nothing that I needed to come to the office and connect to your computer. You connected a perfectly legit KVM to your computer, and that's it. You got a keylogger in there. That would be incredibly hard to detect, right? Well, we thought that this is a great research subject, and we started researching it. And in order to research that, the first thing we need to do is to get a KVM. So we went to the store next to our office and bought ourselves a KVM, took the box, went to the office, and happily opened it and started unpacking it. First thing we find in there is manuals, it's cables, it's warranties, and a CD. Now, that CD contained a few very interesting files. One of them is called a firmware upgrade utility. And the other one, very conveniently named firmware.bin. Okay, we were thinking this is going to be a bit too easy. So we started looking at this firmware.bin file, and we actually find out that this thing has a really high entropy levels. So that practically means that it's either encrypted or compressed in some way that we can't really decompress. So we were thinking, okay, both me and Lior, the other guy that made this research, we are both pretty experienced x86 guys. So all we need to do is to reverse engineer the firmware upgrade utility, yeah, and what we are expecting to see is that the firmware.bin file will be loaded, yeah, then it will be like decompressed and open, and maybe we can find it. However, this utility is a huge utility. It has thousands and thousands of functions. It's a C++ code full of vtables, really a big mess, and we didn't really want to deal with it. But when we ran it dynamically in a debugger, we saw the exact behavior that we expected. It actually took this file, sent it to some kind of decompression function, and then stored the output in some kind of memory range in there. So we went to this memory range, and what did we find there? No, challenge accepted, yeah. Well, we met a blob, and this blob looks something like this, right? And this is its image representation. Looks nice. Let's see some of the properties of this blob. So first of all, it's a 64K blob. And that makes sense because 8-bit architecture, 64K, looks okay. And then now this blob has really low entropy, which again confirms our suspicion that it's now decompressed. That's also good. But it has completely not even a single string in it. Nothing at all. Nothing. And that's, we were expecting to see something, some kind of word in there. And having no strings at all is not so good for us. But we go on. And we make some kind of frequency analysis of this. And we try to match it to other firmwares and other assembly languages and stuff like that. And well, nothing even comes close. We don't know what this blob is. So the next thing we do is use our favorite tool, in these cases, binwalk. Yeah, for those of you who are not familiar with binwalk, it's kind of a tool that when you enter a binary blob in there, it will check it for signatures and known assemblies and known firmwares and stuff like that. But the thing is that binwalk, in this example, had 0 results. I mean, I've never seen something like this. Actually, 0 results, nothing at all, nothing, completely empty. Now, we were sitting, looking at ourselves, looking at this blob, and saying, wow. I mean, what can we do with it? We're kind of lost here. So that entire path of research was a complete failure. And now we were thinking to ourselves again, you know, there's 2 options for us now. One would be to go back to the firmware upgrade utility and reverse engineer the entire thing. It will be a Sisyphic job. It will take us days, weeks, months, I don't know. But we don't really like it. We don't really feel like doing it. So the other thing we come up with is maybe we can be a bit creative about it, a bit innovative. And in order for you to understand what I mean when I say innovative, you must first understand how this firmware upgrade utility actually works, how this firmware upgrade process works. Well, the thing is that you connect this kind of strange serial cable that you take from the box of the KVM. You connect one side of it to the RS-232 port of your computer, and the other side goes into the KVM. You run the utility, and everything is upgraded. The KVM is actually upgraded through this serial cable, right? So we were saying, okay, maybe we can download some kind of generic serial sniffing software and sniff the serial protocol there, and then all we need to do is just to analyze, to understand the serial protocol itself, and hopefully now we will have the firmware going into the device through the serial protocol, right? So that sounds also easy. So challenge accepted. We did just that. So we started sniffing the serial protocol, and we got an output that looks something like this. Now let's analyze this together, just very quickly. So first thing we see here that there are 2 types of messages. The red messages are from the KVM, and the yellow messages are sent to the KVM over the serial cable, right? The first thing we notice is that each of these messages has some kind of fixed header to it, right? The hex value of it is 4655, which is the ASCII representation of FU. All right, so is anybody trying to tell us something here, FU? Well, yes, actually they are trying to tell us something, and that something is firmware upgrade, right? Yes, thank you, thank you. So feeling a bit amused about all this, we went on with the analysis. And the next thing we notice is there's something that looks really suspiciously like an opcode in here. I don't know if you can see, you probably can. It goes like A0, A1, A2, A3, 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 and almost all of this file is actually composed of the A3 messages. So what this tells us that the first part here is some kind of serial handshake going on, and the second part, the big part, is the data. Right? And we are actually interested in the data part of it. So we're going to take a closer look in this now. And the thing about the data, the next thing we notice is there's some kind of sequence number in here. You see, it actually goes 0, 1, 2, 3, 4, 5, 6, up until the end of the file. Whenever there's a retransmission, the number repeats itself. So it seriously looks like a sequence number. And now we have it. And the only thing missing now is something that we expect to see in every serial protocol around the world, and that's some kind of error correction, right? And then we notice that this last byte in all of the messages is actually an accumulative XOR of all the bytes. If you make an accumulative XOR of all the bytes, you get this byte. So this seriously looks like a checksum, and we decided this is our checksum value. And when keeping, there's nothing more we can find. Keeping inspecting this, no more patterns, no more nothing. So we figured out that that's it. We got this string pretty much analyzed. And all we need to do now in order to extract the firmware or the data from the serial protocol is just to, first of all, get rid of the handshake part because it's really not interesting, and then take a look at the data part. Then again, get rid of all the serial related bytes, and then put it all together. And if we take a look at this, then hopefully now we will have our firmware, right? Guess who? It's the same blob. The exact same blob. All this firmware upgrade utility did was just to take this blob and send it over the serial protocol into the device itself. Now, the device is probably responsible of opening this, but we had no way of knowing this, and we can say that that is another great failure. Well, again, feeling a bit depressed about this, we said, well, hey, you know, this thing, this blob, is passed into the device, and then it's probably handled there, right? So the next logical step, the only logical step, would be to, yes, to open up the device. This is how it looks like under the hood, right? Now, our first impression of this, whoa, that's like a lot of electronics in there. We are software guys, not hardware guys. What do we do with this? What can we do with this stuff? And now we're feeling really depressed. And then a few whiskey shots later, we say to ourselves, you know, obviously there's a lot of big chips in there, so maybe we can Google them up. We can try figure out what are these chips. Then maybe it will give us some kind of clue of what this thing is doing, right? So let's do this together now. First thing we notice, two really big chips in here. They have the vendor name engraved on them. Completely no information about them in Google. Big black boxes. We think they're ASICs, just judging by the number of pins they have, but we actually have no clue what they do. And then we find another chip. Now, this chip, we do know what it is. It's a PLD device. Now, PLD, for those of you who don't know, it stands for Programmable Logic Device. Yeah, that's something like you design your own circuit, your own PC, circuit, and then you burn it into the chip, the PLD chip, and then the chip runs your circuit, right? So we do know it's a PLD. We have no idea what it's running, and we don't know how to look for it, so we left it alone for the moment. And then we find something that we know. It's RAM. It's memory. That's great. It's also connected to something called a D-latch. Again, something D-latch, flip-flop. Flip-flop, I remember from my university days. How is it all connected to the picture here? I don't know yet, but anyway, that's a memory, right? And the last chip here was actually the most interesting chip of them all. This chip is an 8052 processor, right? It's an Intel-based chip. It's the next version, the advanced version, the commercial version of another chip called 8051. It runs assembly, and this assembly is called 8051 assembly, right? Well, now we're suspecting of this chip to be the brains behind this device, but we actually don't know what's going on here yet. And this actually got us pretty lost for some time. And we tried figuring out how this all put together, what's going on here. And the question is, we do know the firmware upgrade comes in through this port. This is the serial port I was talking about, right? And then, where does it go to? I mean, it goes somewhere, but where? It can go into the 8052 chip, right? But it can also go into those big black boxes, right? And it can also go into another chips, and it could be divided into chunks, and each chunk goes into different chip. We don't know. We don't know what to do. So what do we do when we don't know what to do? Well, we use Google. And when we used Google, we found this very, very interesting PCB in some kind of Russian KVM review site. I have no idea why, why anybody reviewing a KVM would need to look at the PCB of it, but they had a pretty good picture of it. And you see, there's something really interesting about this one. This is like almost the exact same model as we have. The only thing is that our model, the one that we are researching, has 4 ports, right? And this one has 8 ports. 8 ports, right? Now, look at this. There's something really interesting about it. Those big black boxes I was mentioning before, right? Now, there's 4 of them, yeah? And those PLDs I mentioned before, again, 2 of them. So, double the ports, double the chips. Why is that funny? Okay, double the ports, double the chips. The thing that is not double, the thing that is still single in here is the RAM. And yeah, you guessed it, the 8052 chip. This is a single chip. So this now really, really smells like this thing is the brains behind this entire KVM, right? And now we would like to know how this 8052 chip gets upgraded. It must get upgraded somehow, but how? So it turns out that each one of the 8051, 8052 chips has an integrated UART port in them, right? UART stands for Universal Asynchronous Receive Transmit, some kind of generic serial protocol, right? And the thing is, okay, we know it as a UART, but which IC pins, which of the chip pins are actually responsible for this upgrade? Well, we can answer this question pretty easily by just looking at the specs, right? So we open up the specs of this chip, and we see this, and it clearly states that these chips here, you see the RX and TX pins, are connected through port 3 of the chip to the UART port. So these are our UART pins. Great. Now we only need to inspect what's going on in these pins in order to understand and to see the firmware hopefully coming into this chip. Challenge accepted. So 30 to 45 China mail shipping days later, we can finally use logic. And this thing here, again, for those of you who are not familiar, this is a logic analyzer. Okay, what it does, it just connects to the pins, and you see the actual electronic signals going into these pins, right? They have these nice clips in there. It actually comes with this great postcard saying, "Thank you for your awesomeness." Okay, so we did just that. We plugged the pins into the UX, into the RX and TX ports, and this revealed the UART signals, right? It looks something like this. You see RX and TX, and the third one, again, why is this funny? RX, TX, and the third one, in case you were wondering, is ground, right? In order for us to differentiate between zeros and ones. And that's it, using the awesome UI of Logic Analyzer. We have now, we make the firmware upgrade process, and we reveal the signals going into these pins, into the chip during the firmware upgrade, and we see stuff like this. You see, we see some kind of pattern here. You see there's stuff going from the UART, and there's stuff going to the UART. Yeah, and if we zoom out of this picture for a second, then we see an obvious pattern. I mean, this stuff is going to the UART, you see, and this stuff is going from the UART. So it goes from the UART to the UART, from the UART to the UART. Again, this seriously looks like a protocol, right? So we take all the signals that we could gather from this UI, and we just put them in the right order. And yeah, somebody is laughing. What do we find? Yeah. It's the same serial protocol. So, what? Thank you. What's going on here is that the serial protocol is connected to the KVM, and then the lines go directly into the 8052 chip, right? So again, everything is probably decoded inside the chip itself. So now we need to, to some kind of chemicals and to open the chip, and no, we don't want to deal with that. So this is now a great failure, right? Or is it? I mean, yeah, it is a great failure, but there is something that we know now that we didn't know before. The thing that we know now is that this thing, this blob that we see, must be actually translated somehow into 8051 assembly. Yeah, now we know the destination language of this gibberish that we see, right? So this gives us some kind of hint here. And what we can try and do, as I said, yeah? And what we can try and do is to try and break this code and break this obfuscation, because obviously it's an obfuscation, it's not encrypted, the entropy levels are low, so we are expecting to see an obfuscation, and maybe now, since we know the destination language, maybe we can try and break it. So, challenge accepted. Let's try to do that. Let's take another look at our blob. Not sure if you remember it. It looks something like this. Now, for those of you who has really, really good eyesight, you might have noticed that the end of this blob is actually composed of the same hex value. See, in this case, 53, 53, 53. So when we see stuff like this, what do we do? What do we do? Yeah, we usually do an XOR operation on that, right? And what we expect is that somebody did an XOR operation, and the original thing was one of two things. Either a NOP sled, just a lot of NOPs, or a zero padding, just a lot of zeros. And luckily, in our case, 8051 NOP is 0. So we just need to XOR this thing with 53, and that's it. We get this really nice blob that looks like this. Still, no strings, no nothing, but you know what? Let's give it a try. Let's try opening it in IDA, in our disassembler, and try to disassemble it as a 8051 code and see what we get. Yes, we get assembly code. That is perfect. We are really happy now, and we're going to our office and starting to, reverse engineer this and try to understand what it's doing. And like just 2 or 3 minutes later, we meet up at the kitchen again and say to ourselves, hey, something here is not so good. And you see, let me show you an example. You see here, the last two instructions, move A R6, move A R6. Now, I'm not a big genius about 8051, but maybe they need to perform the same operation twice in order to make sure it works. Well, no, the answer is obviously no. So we have a feeling of what's going on here, so we made a little test. We took calc.exe, which is obviously an x86 code, right? And we tried to disassemble it as 8051 assembly. And what do you know? Again, we got proper assembly. Oh, okay. So this starts to look a bit strange. So what we did in order to verify our assumption is take this picture of a cat and load it into IDA as 8051 assembly. And what do you know? Proper assembly. Yeah, there's functions, there's everything here. And that's... Thank you. Now, this is the moment that we actually realize that if you really try hard enough, everything is 8051 assembly. Okay, let's be serious again. Now, back to our blob, back to step 1, or maybe square 2, because we decided to keep the XOR operation because it looks like something good to do. But the thing now that, again, those of you with good eyesight might have noticed that the last 8 bytes of this blob are actually different. Yeah? But what are they? What are those bytes? Are they a clue? Yeah? Is this some kind of clue left to us by an embedded developer? What can we do with them? Well, the first thing that comes to mind is error correction. Yeah, they are in the end of the file, so maybe there are some kind of error correction. So we take these bytes and try to check them for checksum, CRC, Adler, MD5, a lot of other error corrections, and no, nothing even comes close. So it's probably not an error correction, at least not a known one. And then we understand that up till now, we've only looked at one version of the firmware, right? We can take a look maybe at the last 8 bytes of a lot of firmware upgrade firmware versions because the vendor lets us just download how many firmware versions that we want. So these are all the 8 bytes from a lot of different versions, right? They are all different. And look at this. Something here just, it looks strange, you see? Because look at this. The byte A1 appears 17 times, right? This is not random. There's some kind of data in here. We just need to understand what it is. But how? How do we do this? So this was actually the eureka moment for our project. What we decided to do is to write those 8 bytes just next to the firmware version, right? So this is from the 3.3.312 and whatever, right? And look at this. There's some kind of obvious pattern in here. You see, the byte 99 appears 3 times in here, and the number 3 appears 3 times in here, right? And and the byte A1 appears twice here, and then the number 4 appears twice here. Well, also the number 1 appears twice, but we actually know it's 4 because it's actually consistent throughout the entire table, right? So we got some kind of mapping between bytes and the number in the version, right? Well, is there a pattern here, right? What can we do? Maybe if we, list, the digits that we see 1 and the hex value that we see 89, this is our mapping, and the binary values, maybe this will give us some kind of clue, right? Look at this. Look at the binary values. There's an obvious pattern here. This part here is fixed, and this part here is not. And not only that it's not fixed, but it's some kind of counter, right? Look at this, 1, 2, 3, 4, binary counter, right? And then we're thinking to ourselves, wait, a counter, well, why is a counter, what is it doing in the middle of the bytes here? It should be in the right hand, so let's shift it or rotate it to the right by 3. And when we did this, this is what we got. And this is the X values of this binary value. And for those of you whose ASCII foo is a bit lacking, then yes, these are the same ASCII values as the digits, right? So all we need to do is to take this blob and rotate its entire bytes by 3, 8 chunks of bytes by 3. And what do we get? We get this, right? This looks much better. This looks like strings now. We are so happy about it. But looking about this a bit more, the strings, they don't look exactly right. Look at this. Look at this example. This is like an, alphanumeric string, yeah? It's just in the wrong order. And I mean, take a look at this again. This is the same string that we saw before, right? There's some kind of shuffling going on here. And if you stare at this long enough, you'll understand that this shuffling is going on in chunk of 8 bytes. Let me explain this a bit better. These are the chunk of 8 bytes, right? And the bytes are actually not in order, but only within their same chunk. Now look at this. Yeah, the byte A is in the right, the A is in the right place, the A, the I, and the Q. Now the G, the O, and the W needs to be moved from the 2nd position to the 7th position. And this goes on and on and on, and it's consistent throughout the entire blob, right? So what we got ourselves is some kind of permutation table. And if we'll apply this permutation table on the entire blob, what will we get? Yes, assembly, proper assembly. This is our firmware. Yes, thank you. Now, it's not over yet. Usually when we do reverse engineering of x86, so the first thing we do is load it up in a disassembler. And the funny thing is, in hardware, the last thing that you do is open it in a disassembler. So it was really, from here, it was really fun. And now, this is an 8051 assembly, so all we need to do is to understand 8051. So we can now actually design our own custom firmware if we can understand this. And all we need to do is just to understand 8051. And for those of you who don't know, we prepared a short review of 8051 assembly. The thing is that it has only 255 opcodes and around 40 instructions. Really a pretty easy assembly to learn. The thing is that functions in this assembly are not really functions. Code jumps into the middle of functions, and from the middle of functions, a whole lot of spaghetti code we didn't really understand. And then there's only a single memory access register. Whenever you want to access memory, you store it in this register and then move the memory. Big mess. And then registers, for some reason, keep changing in the middle of the code, of the execution. That's because there's some kind of register banks. It's a nice idea. But anyway, we gave this 1.5 stars out of 5. x86 is still much better, in our opinion. And that's it. Once we have understood this, we can properly analyze this code. And this is a screenshot from IDA, from our disassembler, and it presents the main function of this KVM. Now, it's divided into a few interesting parts. One is HID parsing. Now, HID stands for Human Interface Device, right? This is what we were looking for. This is where the actual keystrokes are being processed. And then this place here processes hotkeys, like if you press some kind of hotkey, it switches the port and stuff like this. And this part here actually controls the LEDs of the keyboard, like the LEDs. For some functionalities, it has to flash the LEDs and stuff like this. And then this part was the really interesting part. You see, this part is a keyboard emulation. So this is where we understand that this KVM is not simply imitating a keyboard. It is a keyboard. It is emulating a keyboard. Do you understand? I mean, this means that we can actually put some kind of rubber ducky inside our KVM. It's an actual keyboard, right? This is amazing. We can type whatever keystrokes we want into the machine, right? So we prepared a little demo, and if you don't understand the implications, I will show it to you now. So we have two networks, two air-gapped networks. One will be an internet-connected network, and the other will be an air-gapped network, 100% secure, as this sticker says. Now, a lot of people, a lot of engineers worked days and nights in order to secure those environments and keep them totally separated from each other by doing a lot of interesting stuff. And they did it really nicely. But the thing is that at the end of the day, a user needs to work on both of these networks, right? And if there's a user, there are computers. And if there are computers, there are videos and mice and keyboards. And the user is, again, frustrated. So he goes to his purchasing department and purchases a KVM, right? And when he did that, then he doesn't need those two sets of keyboard, video, and mouse. He only needs one. Now his life is easy, right? So what will happen if this KVM is malicious? If it contains our malicious firmware? This KVM can wake up in the middle of the night, right? Just in the middle of the night, and start typing on the user password on the internet connected network, right? Now, some of you might be asking yourself, wait. The computer is password protected. How does it know the password? And I ask you back, well, how do you enter your password? To your keyboard? Yes. So the KVM already knows this. It types in the password, and then it performs like a wget or something, and gets the malicious virus from the cloud, from the internet, into the internet-connected computer. Now that's perfect persistency, right? Look at this. There's nothing you can do in order to prevent this attack. I mean, you can reformat your hard drive, you can switch your computer, and again, as long as the KVM is there, every night you will get infected again and again, right? This is cool, but this is not cool enough, because we want to get into the air-gapped network. So what we did is design a very special malware, which what it does when it's ran on the computer, it actually replicates itself, and when it replicates itself, it then starts typing itself into the computer. And when doing this, our agent gets these keystrokes and passes this malware into the memory of the KVM. Then he very casually switches the ports and retypes this malware into the other network. And so we got now two malwares, two of the same malwares in both of the networks, and effectively bridging the gap between those networks. Those are no longer air-gapped networks, right? Air-gapped networks. So this is what we did, and now I have a little demo for you. Hopefully it will work. I'm holding my fingers. I'll put this down for a second. Never mind. I'm doing fine. Can you hear me? I'll keep using this. Okay. So what you see now is the output of the attacked computer, right? I have here two computers. One is the attacker, the internet-connected one, and the other one is the attacked, the air-gapped network computer, right? And they are only connected through this KVM I have on the desk. No other connections between them, only through a KVM, right? Now look at this. This is the attacker computer. I just need to run my malware here. Let me just lock the screen. Let's see what will happen. He woke up. No hands. Whoa. Now, the thing is that well, you're laughing, but this is actually a really neat trick that we actually needed to type the binary into the attacked computer, right? And the way to do that is to use base64. And what we used is certutil, which is a default utility that comes with any Windows installation. And we just typed the base64 of our malware into this. Yeah, we save it as a text file and then decoded, and then we got a binary, actual binary on the computer. Now, It's not a big file, but it will take a bit to work. So if anyone has any jokes, no? Okay. It will finish soon. 20 more minutes? Come on, come on. Okay. Looks like it's gonna finish soon. I could have. But this is a live demo, man. Give me some respect for that. That's it. We have our text file. And now, and the certificate into encoded.txt. Go on, go on. Now certutil decodes it into decoded.bin, which is our malicious file, very malicious. And now we run it. And yes. Thank you very much. Thank you very much. So air-gapped networks are not really air-gapped as you thought if you have a KVM connected to them. And if I'm lucky enough, there's one more thing my malicious software knows how to do. Let's see if it works. Back to our presentation. So I'm running out of time, so let's do it quickly. So what are the attack vectors? So some of you might be asking yourselves, hey, you need to have physical access to the KVM. And that's right, I needed to have physical access to the KVM. Still, with physical access, we have a few attack vectors that are really reliable. One of them would be, just give me 30 seconds alone with your KVM, and that's it. And the other one would be, let's attack the supply chain. Yeah, the seller of the seller of the seller that sells you the KVM. We can just switch it, and you get a malicious KVM right out of the box. That's nice, and that's been known to be done before. Now, however, there are many KVMs, not the one that we researched, that are being upgraded through IP. And if they are upgraded through IP, then theoretically, we can exploit the same thing remotely. That would be really, really, really cool to do, and it is possible. And the thing is that KVMs are really not exploit-proof. I mean, just Googling it up a bit, these all CVEs are related to KVMs that are upgraded via Ethernet and via IP. So it is really possible, just it was out of our scope of research to do. Now, what can you do to protect yourself from these kind of attacks? First of all, know your environment. That's the best suggestion I can give you. I mean, sometimes it's not necessary to connect a really secured computer to a non-secured computer through a KVM. And if it's not required, then please remember this and don't do this. But sometimes, of course, it's unavoidable, and you need to do this. And if you do this, know that there are some other creatures called secured KVMs. Now, those creatures look like this, and they actually close all of our attack surface. They don't let us do anything from what we've shown. The thing is that those devices cost like 100 times more than normal KVMs, and I actually know very, very few people who actually buy this stuff, right? So if you do need to connect something really, really important, then you might consider buying one of these. And the last thing is be innovative. And by being innovative, I mean, we sat down and we thought a bit about what can we do in order to protect against this? What we came up with is a nice idea. It's not perfect, but it's nice. What we do is we wrote a small agent that you can place on your computer. And this agent actually logs keystrokes. It doesn't log the keystrokes themselves, but the statistics. And what it looks for is some deviation from the normal statistics, right? What we did here is type a lot of keystrokes really, really fast. That's a deviation, right? So if we detect some kind of deviation, like not using backspaces, or the intervals between the characters are really, really small, then something weird is going on, and all we need to do is just to pop a message box, and this will fuck up the entire exploitation process. That's a nice idea. You might have better ones, but we did it with the help of our colleague Dror Rappaport. Thanks, Dror. And that's about it, guys. That's my presentation. Thank you.
Thank you. Thank you very, very much for this very entertaining and fun presentation. So if you have any questions, come to the microphones. Here's one and there's one. And ask your questions. You can also ask them via the internet. I think there are also questions on the internet. So maybe we start here with you. The other ones who are leaving this room, please be quiet because there is still a question and answer session here. So please be quiet while leaving this room. Thank you. Okay, your question. This doesn't work.
You want mine?
I can give. Oh, is it
Hello?
on? Yeah.
Hello. So now, thank you very much for the talk, very great. My question is, how much time did you need to achieve this goal? How many days, weeks, or is there a number?
It's a good question because we worked on it on and off. So overall, it took us I think 6 months, but it's not a straight job, yeah, just with peaks.
Okay, thank you.
Question over here.
I could think of just another attack surface because even if your KVM doesn't update over the internet, if it has USB for keyboard and mouse and not PS2, then maybe you could even flash a new firmware just by exploiting some USB functionality, like bad USB.
Thank you. This is my next research.
Okay.
A question from the internet?
Yeah, we got a few questions. One is, can you upgrade the KVM via the connected USB keyboard? Just typing in just a dongle or something like that?
Not that I know of.
And also another question, what are the black boxes in the slides? Some people ask for that.
I still don't know.
Thank you. So
But they probably has something to do with the outputs, right? I think there are video chips related to video chips or something like this.
thank you. Over here again.
You said you could copy the code you got over the internet in a night. How long would it approximately take to type in the code?
It depends on the timer of the KVM and how long is the intervals between the keystrokes. So it varies between one type of KVM to the other. This KVM is pretty slow, and if you want to download a big executable, I'm guessing that something like 30 minutes.
Okay.
But there are other KVMs that might take 5 minutes or even less.
Okay, thanks.
And over there again.
I wonder whether you have thought about implementing bidirectional communication, for example, by flashing the keyboard LEDs.
We thought about it, and we even tried to do something, but we couldn't really make anything. It would be really cool if we could, though.
Okay, thank you.
And another question from the internet.
Two questions. The black boxes wasn't meant as the chips. The black boxes was meant for the censorship of the images.
I'm sorry, can you repeat the question? I didn't understand.
You had some images in a hex dump, and the people were asking why was it censored?
That's the vendor name.
Okay.
Sorry.
Another question, is there any way to shut down the internal keyboard, or is this a core feature?
No, that's a feature of the KVM.
Okay.
Is it possible to emulate a virtual Ethernet device via the KVM? So you could really make a bridge between those air-gapped networks?
Whoa. I saw something very similar talk at DEF CON this year. We couldn't do it. I would be really happy to try and do something like this, but we didn't try.
Okay, thanks.
Are there any more questions? I can't see anybody. So thank you again, Janif,
Thank you.
very much. Give him a warm applause.